Right, the actual integration of this question was fairly straightforward. It was the thinking about how to get started and what's going on that made this a bit more complicated. Now, you've got this shape in polar coordinates, and you first of all need to work out which areas we actually need and what's going on with the curve. Now, you could use your calculators to help you with this and see it being drawn. One way, which would work in either calculator, is to do a table of values if you're not sure how this is going to work. So you can think about it and work it out. You can just do a table of values. So I've done a very quick one here where I've gone 0, pi over 2, pi, etc. And I can see what's happening to the radius at any point. So if I scroll down, I can see, so that's pi over 2, it's getting larger. At pi, we've got a bit larger, and then it continues to get larger. Okay, going round, so 9 volts, there we go, so that was 2 pi, so now we're at 3 pi, and then you can see it starts to come back in again. And you can use this to help you work out what's going on with the curve. So what's going on with the curve is it starts here, it loops out, we go out, we go round the edge, and then we start spiraling back in again, like that. They also then need to work out what we're doing with my areas. Now, actually, what's easiest with this, if you look, this shape is completely symmetrical, so that can save us a bit of work. And then if you look at your table, when you think about it, when I first looped here, I started at 0 up to 2 pi, that's pi. So this section is 0 to pi. My next section then goes from here to here. So this section I'm going from pi to 2 pi. And then I go out here. Okay, so along this section of the curve, I'm going from 2 pi to 3 pi. Now what's going to happen if I integrate, so if I integrate between 0 and pi, I'm going to get that little shaded bit, which is symmetrical to the other shaded bit. If I integrate between pi and 2 pi, I'm going to get all of this area. Now that's going to help me because that's the same as this area here, including that bit that I've shaded. And then if I do the last integration between 2 pi and 3, that's going to get me the entire half here, the top half, which looks a bit like a circle but isn't quite. So I want to get all the shaded bits. So the first shaded bit is the integral between 0 and pi. And I'm going to need 2 of that area, whatever that gets me. This isn't the proper formula, this is just my thinking. I'm also going to want 2 lots of the integral between 2 pi and 3 pi. Okay. But the problem there is that's not going to give me just this section, it's going to give me that section plus all of this. And that means I'm going to end up counting the bit I've already done between 0 and pi again, and I'm going to include the white bit. But if I take off, I'm doubling everything because I'm doing 1/2 and then I need to double it for the other half. If I take off the integral between pi and 2 pi, the integral between pi and 2 pi gives me the white bit and the inside shaded bit. So if I do all of that mess, I'm going to end up with the shaded bit left. Okay, so remembering that's 0 to pi, then I've got pi to 2 pi, and then I've got 2 pi to 3 pi. Okay, once I've done that, I'm going to go to the formula book and find out what my actual proper formula is, and the area of the sector is a half integral of r squared d theta. Well, what I'm going to focus on to start with is all these are going to be integrating the same curve. So let's just work out the integral of r squared d theta, and then I can sub that in. So that's going to be the integral of sine squared theta over 6 d theta. Now this should be familiar to you from your maths A level. So if we see a sine squared, a useful thing is to use a double angle formulae to think about that. So you can remember that cos 2a is the same as 1 minus 2 sine squared a. So if you rearrange that, okay, so all I'm going to do is now apply that to my situation here. So that's going to be a half 1 minus cos. I'm going to double the angle. So then I can quite easily integrate that. And there would be plus a constant if I had no limits. Now I'm going to substitute that into my proper formula. So the area is going to be, now you can see I'm doubling all of my areas. I'll put that at the front. So that's going to be 2 times a half for the formula of a half integral of r squared d theta. And then I'm going to take my expression here, that's my integral. You can see that's got a half at the front, so I'm just going to move that to the half at the front. And then what I need now is just this integral between each set of limits, so between 0 and pi. And then I'm going to add on between 2 pi and 3 pi. Right? And then I'm going to subtract between pi and 2 pi, like that. Note, there are different limits you could use because each section is repeated twice, so you could use the limits from the other section if you preferred. And I think in the mark scheme, actually one of those is slightly different. If you then work all that out, so being careful, substituting your numbers in, you'll actually find a lot of it cancels out, and at the end you get that the area was pi over 2. Okay, once we found that out, and it's worth getting an answer so that we can do the second part, they're now going to scale this up. So the width of the logo is 12 meters. And then this has some info about paint, and we want to know how many tins of paint we need. Right, so if we go back and have a look at our diagram, okay, the width that we want is going to be 12 meters. Now we need to find out how wide it is to start with. So this point here is when you rotate round, and we've gone round. Once we go around there, so that's pi, then we go 2 pi, so that's when theta equals 3 pi. So when theta equals 3 pi, r equals sine 3 pi over 6, which is a half pi, so that's 1. This point here then, when did we get there? Well, we started there, we went round the loop, and we got there, so theta is 2 pi, will give us that point, so that's r sine 2 pi over 6, which gives us root 3 over 2. Right, so our current total width is 1 plus root 3 over 2. Okay. So on the diagram, width equals 1 plus root 3 over 2. In real life, we've got 12 meters. So our scale factor for the length is 12 divided by 1 plus root 3 over 2, which comes out to be this. Right, what do we then want to do? Well, we now want to scale up our area. So area of paint needed is our current area times our linear scale factor squared, because we're doing area. And then if you read the question carefully, we need 2 coats of paint, so I'm going to need to double that. Now we might as well go to a decimal because we're going to need that anyway, so that's 129.92 metres squared. Okay. So we're just going to take our area. It says each paint covers 30 metres squared, and you'll get 4.32. So therefore, obviously we're going to need 5 tins of paint.